Pythagoras Theorem. Pythagoras Theorem, as in Euclidean geometry, gives the relation between the sides of a right-angled triangle. That is, hypotenuse square is equal to base square plus height square. As we have studied about the property of similarity of right-angled triangles, we will prove the theorem using the same. Let's look at the theorem now. In a right-angled triangle, the square of hypotenuse is equal to the sum of the squares of the remaining two sides. Given, in right-angled triangle ABC, angle ABC is equal to 90 degrees. We have to prove that AC square is equal to AB square plus BC square. Construction: draw a segment BD perpendicular to hypotenuse AC in point D such that D lies between A and C. Proof: in triangle ABC, segment BD is perpendicular to hypotenuse AC by construction. Therefore, triangle ABC is similar to triangle ADB by property of similarity in right-angled triangles. Therefore, AB upon AD is equal to AC upon AB is equal to AC upon AB, as they are the corresponding sides of similar triangles. Therefore, AB square is equal to AC into AD. Let us call this as statement 1. Similarly, we have triangle ABC similar to triangle BDC. Therefore, BC upon DC is equal to AC upon BC, as they are the corresponding sides of similar triangles. Therefore, BC square is equal to AC into DC. Let us call this as statement 2. By adding 1 and 2, we get AB square plus BC square is equal to AC into AD plus AC into DC is equal to AC into AD plus DC is equal to AC into AC, since D lies between A and C, is equal to AC square. Therefore, AB square plus BC square is equal to AC square. Hence, in a right-angled triangle, the square of hypotenuse is equal to the sum of the squares on the remaining sides. Converse of Pythagoras Theorem. In a triangle, if the square of one side is equal to the sum of the squares of remaining two sides, then the angle opposite to the first side is a right angle and triangle is right-angled triangle. Here we are given in triangle ABC, AC square is equal to AB square plus BC square. We need to prove that angle B is equal to 90 degrees. That is, triangle ABC is a right-angled triangle. Let us construct a triangle PQR such that QR is equal to BC, PQ is equal to AB, and angle Q is 90 degrees. Proof: in triangle PQR, angle Q is a right-angled triangle by construction. Therefore, by Pythagoras theorem, PR square is equal to PQ square plus QR square. By construction, we get PR square is equal to AB square plus BC square. But it is given that AC square is equal to AB square plus BC square. Therefore, PR square is equal to AC square. Therefore, PR is equal to AC. Let us call this statement 1. Now, in triangle ABC and triangle PQR, segment AB is congruent to segment PQ by construction. Segment BC is congruent to segment QR by construction. And segment AC is congruent to segment PR from statement 1. Therefore, triangle ABC is congruent to triangle PQR by SSS test of congruency. Therefore, angle ABC is congruent to angle PQR as they are the corresponding angles of corresponding triangles. But angle PQR is equal to 90 degrees by construction. Therefore, angle ABC is equal to 90 degrees. Therefore, triangle ABC is a right-angled triangle. Hence, it is proved that in a triangle, if the square of one side is equal to the sum of the squares of the remaining two sides, then the angle opposite to the first side is a right angle and the triangle is right-angled triangle. Note: while we call it Pythagoras theorem, it is also known to Indian, Greek, Chinese and Babylonian mathematicians well before Pythagoras lived. Let's study the proofs of Pythagoras theorem by Indian mathematicians. Bhaskaracharya was one of the most important Hindu mathematician of the 2nd century AD. He used the following diagram in proving the theorem. Area of triangles is equal to 4 into bracket 1 upon 2 AB. Area of small square is equal to B minus A whole square. Area of big square is equal to area of triangle plus area of small square. C square is equal to 4 into bracket 1 upon 2AB plus B minus A whole square. C square is equal to 2AB plus B square minus 2AB plus A square is equal to B square plus A square. He used the property of similarity and proved this theorem from the proof. Note: it is conventional to consider the length of the side opposite to vertex A as small a, vertex B as small b, and vertex C as small c in triangle ABC. Let us look at few examples. Example 1. Sides of triangles are given below. Determine which of them are right-angled triangles. In case of a right-angled triangle, write the length of its hypotenuse. Number 1. 7 cm, 24 cm, 25 cm. Solution. The sides of the triangle are 7 cm, 24 cm, 25 cm. The longest side is 25 cm. 25 square is equal to 625. Mark this statement as 1. Now let us calculate the sum of the squares of the other two sides. 7 square plus 24 square is equal to 49 plus 576 is equal to 625. Mark this statement as 2. From statement 1 and 2, we get 25 square is equal to 7 square plus 24 square. Therefore, these are the sides of a right-angled triangle by the converse of Pythagoras theorem. Length of the hypotenuse is 25 centimeters. Number 2. 50 centimeters, 80 centimeters, 100 centimeters. Solution. The sides of the triangle are 50 centimeters, 80 centimeters and 100 centimeters. Therefore, the longest side is 100 centimeters. 100 square is equal to 10,000. Mark this as statement 1. Now, the sum of the squares of the other two sides will be 50 square plus 80 square is equal to 2,500 plus 6,400 is equal to 8,900. Mark this as statement 2. From statement 1 and 2, we get 100 square is not equal to 50 square plus 80 square. Therefore, the given sides do not form right-angled triangle. Number 3. 20 centimeters, 16 centimeters, 12 centimeters. Solution. The sides of the triangle are 20 centimeters, 16 centimeters, 12 centimeters. The longest side is 20 centimeters. 20 square is equal to 400. Mark this as statement 1. Now, let us calculate the sum of the squares of the other two sides. 16 square plus 12 square is equal to 256 plus 144 is equal to 400. Mark this as statement 2. Therefore, from statement 1 and 2, we get 20 square is equal to 16 square plus 12 square. Therefore, these are the sides of a right-angled triangle by the converse of Pythagoras theorem. Length of the hypotenuse is 20 centimeters. Example 2. In triangle ABC, if segment AD is perpendicular to side BC, then prove that AB square plus CD square is equal to BD square plus AC square. Solution. In triangle ABD, we have angle ADB is equal to 90 degrees. Therefore, AB square is equal to AD square plus BD square by Pythagoras theorem. Let us mark this equation as 1. In triangle ADC, we have angle ADC is equal to 90 degrees. Therefore, AC square is equal to AD square plus CD square by Pythagoras theorem. Let us mark this equation as 2. Now, by subtracting 2 from 1, AB square minus AC square is equal to BD square minus CD square. That is, AB square plus CD square is equal to BD square plus AC square. Example 3. Triangle PQR is an isosceles triangle with segment PR is equal to segment QR. If PQ square is equal to 2PR square, then prove that triangle PQR is a right triangle. Solution. It is given that PQ square is equal to 2PR square is equal to PR square plus PR square. Therefore, PQ square is equal to PR square plus QR square, as it is given that PR is equal to QR. By converse of Pythagoras theorem, PQ is the longest side and angle R is a right angle. Therefore, PQR is a right triangle. Example 4. Segment AN and segment CM are the median of triangle ABC, in which angle B is equal to 90 degrees. Prove that 4 in bracket AN square plus CM square is equal to 5 AC square. Solution. In triangle ABC, AC square is equal to AB square plus BC square by Pythagoras theorem. Let us mark this as 1. In triangle ABN, according to the Pythagoras theorem, AN square is equal to AB square plus BN square is equal to AB square plus 1 upon 2 BC square, as N is the midpoint. AN square is equal to AB square plus 1 upon 4 BC square. Therefore, 4AN square is equal to 4AB square plus BC square. Mark this as statement 2. In triangle CBM, according to the Pythagoras theorem, CM square is equal to BC square plus BM square is equal to BC square plus 1 upon 2AB square, as M is the midpoint. CM square is equal to BC square plus 1 upon 4 AB square. Therefore, 4CM square is equal to 4BC square plus AB square. mark this as statement 3. Now, by adding 2 and 3, we get 4an square plus 4cm square is equal to 4ab square plus bc square plus 4bc square plus ab square is equal to 5 in bracket ab square plus bc square. Therefore, 4 in bracket an square plus cm square is equal to 5ac square from statement 1. Example 5. E is a point on hypotenuse DF of triangle DFH such that segment HE is perpendicular to segment DF. Segment EG is perpendicular to segment FH and segment EK is perpendicular to segment DH. Prove that number 1, EG square is equal to FG into EK. Number 2, EK square is equal to DK into EG. Solution. It is given that EG is perpendicular to FH and EK is perpendicular to DH. Angle H is equal to 90 degrees. Therefore, quadrilateral EKHG is a rectangle as all angles are right angles. Therefore, EK is equal to GH and EG is equal to KH as they are the opposite sides of a rectangle. Let us mark this as statement 1. Now, segment EG is perpendicular to segment FH. Therefore, EG square is equal to FG into GH as EG is geometric mean. EG square is equal to FG into EK from statement 1. Similarly, EK square is equal to DK into KH as EK is geometric mean. Therefore, EK square is equal to DK into EG from statement 1. Example 6. Sides of a rhombus is 10 cm and one of the diagonals is 16 cm. Find the length of the other diagonal. Solution. Quadrilateral PQRS is a rhombus. Its diagonals PR and QS intersect each other at point T. By properties of diagonals in a rhombus, segment PR is perpendicular to segment QS, PT is equal to TR, ST is equal to QT. Let SQ is equal to 16 centimeters. Now, SQ is equal to ST plus TQ as point T lies between points S and Q. Therefore, 16 is equal to ST plus ST. 16 is equal to 2ST. Therefore, ST is equal to 8 centimeters. In triangle PST, angle T is equal to 90 degrees. PS is equal to 10 centimeters. ST is equal to 8 centimeters. Therefore, PS square is equal to ST square plus PT square by Pythagoras theorem. Therefore, 10 square is equal to 8 square plus PT square. Therefore, 100 minus 64 is equal to PT square. Therefore, 36 is equal to PT square. Therefore, PT is equal to 6 centimeters. Now, PR is equal to 2 into PT is equal to 2 into 6. Therefore, PR is equal to 12 centimeters. Thus, length of the other diagonal is 12 centimeters. Square root spiral. Look at the wonderful design found in nature. This one is produced by drawing right angles with one of the right arms in increasing lengths continuously. Let's start with exercise 1.5. Question 1. A ladder 10 meter long reaches a window 8 meter above the ground. Find the distance of the foot of the ladder from the base of the wall. Solution. Let us assume that AB is ladder and B is the window at 8 meters from ground. Triangle ABC is right angled at C. Therefore, by Pythagoras theorem, AB square is equal to AC square plus BC square. Now, by substituting the value of AB is equal to 10 and BC is equal to 8, we get 10 square is equal to AC square plus 8 square. AC square is equal to 100 minus 64. AC square is equal to 36. Therefore, AC is equal to 6. Hence, the foot of the ladder is 6 meters away from the wall. Question 2. Prove that the sum of the squares of the sides of a rhombus is equal to the sum of the squares of its diagonals. Given ABCD is a rhombus. To prove AB square plus BC square plus CD square plus DA square is equal to AC square plus BD square. Solution. Let the diagonals AC and BD of ABCD intersect at point O. We know diagonals of rhombus bisect each other at right angles. Therefore, angle AOB is equal to angle BOC is equal to angle COD is equal to angle DOA is equal to 90 degrees. And OA is equal to OC and OB is equal to OD. In triangle AOB, angle O is equal to 90 degrees. Therefore, AB square is equal to AO square plus BO square. Therefore, AB square is equal to half AC square plus half BD square. AB square is equal to AC square upon 4 plus BD square upon 4. Therefore, 4AB square is equal to AC square plus BD square. Let us mark this as statement 1. Similarly, we have 4BC square is equal to AC square plus BD square. Let us mark this as statement 2. 4CD square is equal to AC square plus BD square. Let us mark this as statement 3. 4AD square is equal to AC square plus BD square. Let us mark this as statement 4. Now by adding statement 1 to 4, we get 4 in bracket AB square plus BC square plus CD square plus AD square is equal to 4 in bracket AC square plus BD square. Therefore, on simplifying we get AB square plus BC square plus CD square plus DA square is equal to AC square plus BD square. Question 3. The perpendicular AD on the base BC of triangle ABC intersects BC at D so that BD is equal to 3CD. Prove that 2AB square is equal to 2AC square plus BC square. Given BD is equal to 3 times CD. But we know BC is equal to BD plus DC. BC is equal to 3CD plus CD is equal to 4CD. Solution. But CD is equal to 1 upon 4 BC. Hence, CD is equal to 1 upon 4 BC and BD is equal to 3 CD. Therefore, BD upon 3 is equal to 1 upon 4 BC. BD is equal to 3 upon 4 BC. Let us assume this as statement 1. In triangle ABD, angle D is a right angle. Therefore, AB square is equal to AD square plus BD square. Let us assume this as statement 2. In triangle ACD, angle D is a right angle. Therefore, AC square is equal to AD square plus CD square. Let us assume this as statement 3. Now, by subtracting 3 from 2, we get AB square minus AC square is equal to AD square plus BD square minus AD square minus CD square. Therefore, AB square minus AC square is equal to BD square minus CD square. Therefore, AB square minus AC square is equal to 3 upon 4 BC square minus 1 upon 4 BC square, since CD is equal to 1 upon 4 BC and BD is equal to 3 upon 4 BC. AB square minus AC square is equal to 9 upon 16 BC square minus 1 upon 16 BC square. Therefore, AB square minus AC square is equal to half BC square. Therefore, 2 into AB square minus AC square is equal to BC square. Therefore, 2AB square minus 2AC square is equal to BC square. Therefore, 2AB square is equal to 2AC square plus BC square. Question 4. Triangle ABC is a triangle where angle C is equal to 90 degrees. Let BC is equal to small a, CA is equal to small b, and AB is equal to small c, and let P be the length of the perpendicular from C to AB. Prove that number 1, CP is equal to AB. Number 2, 1 upon P square is equal to 1 upon A square plus 1 upon B square. Solution. Number 1, CP is equal to AB. Let CD be perpendicular to AB. CD is equal to P. Area of triangle ABC is equal to half AB into CD is equal to half of CP. Let us call this equation 1. Area of triangle ABC is equal to half BC into AC if BC is the base. Therefore, area of triangle ABC is equal to half into A into B. Let us call this equation 2. Thus, from equation 1 and 2, we get half CP is equal to half AB. By cancelling half, we get CP is equal to AB. Number 2. 1 upon P square is equal to 1 upon A square plus 1 upon B square. Triangle ABC is a right angle triangle with right angle at C. Therefore, AB square is equal to BC square plus AC square. Therefore, C square is equal to A square plus B square. AB upon P whole square is equal to A square plus B square, as CP is equal to AB. C is equal to AB upon P. Therefore, A square into B square upon P square is equal to A square plus B square. Therefore, 1 upon P square is equal to A square plus B square upon A square B square. Therefore, 1 upon P square is equal to 1 upon B square plus 1 upon A square. Thus, 1 upon P square is equal to 1 upon A square plus 1 upon B square.